Awesome. So today's video, we're going to get into the autonomic system, which includes the sympathetic, parasympathetic, and we're also going to compare it to the somatic, somatic nervous system, which is part of the peripheral. So, and I, of course, have my laptop over here with the questions on it, and then that'll help me kind of go through this. So the first one is compare and contrast the sympathetic division of the ANS, the parasympathetic division of the ANS, and the somatic nervous system. Include such things as their points of central nervous system origin, number of neurons in the pathway, location of the ganglia, transmitters, neurotransmitters, types of receptors, and actions. So just to break it down so we understand, so we have the central nervous system, and as soon as it leaves the spinal cord, it becomes the peripheral nervous system. Just for all purposes today, we're just going to call this the somatic. This is the autonomic, and then that will bring us to the peripheral, or the parasympathetic nervous system and the sympathetic nervous system. So when we're breaking these down basically into function, the central nervous system is like our brain, and then our spinal cord, and then our peripheral nervous system branches out of that. So then it breaks it down even more. So our parasympathetic is rest and digest. So normally it's a lot of inhibitory pathways, which relaxes the muscles, and then its counterpart is the sympathetic nervous system, which we've heard is flight or fright. So if we just compare and contrast these two, as if you're being chased like a bear, this is what's going to kick in. It doesn't care about digesting, it doesn't care about those things. It just wants more oxygen, more blood pump into the muscles so you can, get out of there. Whereas the parasympathetic nervous system is just you're just sitting there scrolling on your phone. You don't really need those things to happen. In fact, it's the opposite, where your body just does its own thing. It takes care of itself there. So, and then on the other side, somatic is voluntary muscle contractions or control. There you go. That's good enough. So we have a few things that are different here. So rest and digest, flight or fright, things that you can't really control, and then muscle contraction, so flexing your bicep, that's something that you have control over. So okay, and so we've said, this is a branch off of the central nervous system. So we got our brain here, okay, with the spinal cord here. So our parasympathetic branches from the brain stem, basically. So we have some that come up here into the head, but the main thing is this thing called the vagus nerve that innervates most of the things in our cavity. So, and then we have a few in the sacrum that come and innervate the bladder or the lower colon, large intestine. So that's the parasympathetic. The sympathetic, it originates on this thoracolumbar region, and it comes out here. And something that's interesting about this one is before it reaches your the targeted organ or soft, smooth muscle, it'll come into this ganglia, and then it'll synapse first. And then we have another neuron that will go and go to the target. So like our parasympathetic has a few different divisions, so does our sympathetic. So the upper cavity is called the sympathetic. Okay, and then our lower region does something similar. It has another ganglia, and all these nerves come in here, and it's called the collateral ganglia. And they do their own synapse, and they go out to the intestines, that goes out into the kidney, it goes out into the spleen. But there is one that comes in here, doesn't synapse, comes out of it, and that's in the adrenal gland above the kidney. So, and then that will synapse in the adrenal medulla and with acetylcholine, and then that will cause epinephrine to be made. And then there is a few that come down that don't synapse, that come down here, synapse in the lower region, and then it'll go to like your lower intestines and bladder again. So this stomach region is called the splanchnic region. And the last region on the sympathetic is the spinal region. So these will come out here. Again, they'll synapse in the ganglia, but then these go to your skin. So they don't go into your cavity, they go into your skin. So they innervate things like hair follicles or the pili, sweat glands, and blood vessels. So, yeah. And so it's important to know that this spinal region is only innervated by the sympathetic region. The parasympathetic has nothing to do with these things. It's all the sympathetic. So your parasympathetic doesn't change your blood vessels, only your sympathetic, and same with your sweat glands, hair follicles. So, and the rest of these just go inside the cavity. And so we were talking about at the sympathetic is that they synapse in the ganglia, or in this one case in the target organ itself. But all of the parasympathetic synapse within their organ. So let's say this is also the one to the kidney. It'll make a tiny synapse, and then it'll hit the target that it wants. So if we're gonna describe these, both of these have two neurons. The parasympathetic has a long preganglia nerve, and then or neuron, and then a very short post-ganglia neuron. And so for the sympathetic, it's about the same. It's a medium to long for the preganglia, and then medium to short for the post-ganglia. So, let's see, I think that's a lot on that. Ganglia. Okay. So that is the autonomic system. The somatic nervous system. Is a little bit different. So again, we have the brainstem. The somatic is a motor neuron. And so this one will go innervate skeletal muscle. So we got skeletal muscle here, skeletal muscle here. And unlike the autonomic nervous system, these ones only have one long chain, and they don't synapse. So they don't have a ganglia that they synapse in, and so it's just one neuron that goes all the way to the muscle, and it'll synapse on the muscles, creating what we got in the muscles. They'll create the action potential or the flexing. So that's already a difference right there. And then also, similarly, the somatic nervous system comes out. The spinal cord's on the lateral. No, the anterior horns of the spinal cord, and they'll come out and innervate these. Yep, so there's only one neuron in the pathway. No ganglia in these guys. And then we'll just get into neurotransmitters. Okay, yeah. And we kind of already talked about the actions of them. The somatic is for motor control, moving your arms, stuff like that. Sympathetic is for like fight or flight or fight. And a lot of those are EPSPs, which are excitatory, and which cause the action potentials to take place and cause the start of your smooth muscle. And the parasympathetic is the opposite of that, where they have inhibitory processes, so it relaxes things for rest and digest. And another thing I need to, I guess, point out between the difference between somatic and autonomic is smooth muscle, and somatic is rough or skeletal muscle. So, okay, and then these have different neurotransmitters and receptors. So let's do the sympathetic one first. So we have this guy. Synapse into the target. Okay, cool. Well, good enough. Okay, awesome. So we have this medium to long preganglionic neuron, and then postganglionic neuron. So on this first one, an action potential will take place at this soma. It'll travel down the length of the neuron, and then it'll release a neurotransmitter. The first one that it releases is acetylcholine. So the acetylcholine releases, and it causes another action potential in the next synapse, the postsynaptic region, the dendrites. There is a receptor called, we're going to put into, it's the nicotinic receptor. So the acetylcholine will bind to it. It will create an action potential through the rest of this. And since it's a sympathetic chain, the second thing will be norepinephrine or epinephrine. The neurotransmitter, the second neurotransmitter is norepinephrine or epinephrine. And it'll react with one of these receptors down here. So we have alpha, beta, and delta. And your alpha 1, beta 1 and 3, and delta 1 are all ESPS, so they'll be excitatory. And then alpha 2, beta 2, and delta 2 are all inhibitory. So the evens are going to be inhibitory, IPSP, and then your evens will be, or odds will be excitatory. So then your norepinephrine will connect with one of these receptors, And there's also another nicotinic receptor over here that causes that action potential. So it'll interact with one of these to affect your target organ or muscle. So that's sympathetic. Very similarly is the parasympathetic. Okay, awesome. Okay, similarly is the parasympathetic. So we have this long presynaptic neuron and then a short one after the ganglia. And so we'll have an action potential at the beginning. It does the same thing, releases acetylcholine, binds to the nicotinic receptor, and creates another action potential. Now here's the difference between the two, is this will release acetylcholine again. And so the acetylcholine, there's another N2 nicotinic receptor there. The acetylcholine reacts with the, I forgot how to pronounce it. It's like muscarinic or, sorry, let me just look at the question again. Yeah, I think it's like muscarinic. Yeah, muscarinic. So sorry, I don't know how to pronounce it, but it'll react with those. The norepinephrine reacts with these ones. And so you can kind of see that difference. The only exception that we can see in this formula is in sweat glands, generalized sweat glands. Instead of releasing acetylcholine or norepinephrine, it'll release this acetylcholine up here instead of the norepinephrine. And that'll do the sweat glands and do the inhibiting or not. So, okay, and then also in somatic nerves, it's just a straight line all the way to the target. It'll use the nicotinic receptor, but this one's an N1. N2 is for the autonomic system. N1 is for muscles, skeletal muscles, and it'll also release acetylcholine to react to that. So these are the different pathways with the different types of receptors, different actions. We've kind of already talked about that. Okay, and then it says the next question is discuss cholinergic and adrenergic receptors. Explain the different subdivisions of each type. Give mechanisms of action for each type of receptor. Example, what happens to when the neurotransmitter binds to the receptor. So the cholinergic receptors are this mucineric receptors. Sorry, that is just, I'm trying to get the words down, and so they react with just acetylcholine. And that's how you can tell the difference. And then the adrenergic receptors react with norepinephrine or epinephrine, which is these two. So that's kind of like the divide that we see there. And the nicotinic is obviously a cholinergic, or something like that. I don't know. Anyways, and so we can kind of see that. Explain the different subdivisions. So we'll erase this. So it's kind of easier to see the subdivisions, what they do and stuff. Okay, so the first one is IP3. And these are their pathways, like what happens when something binds to them. Okay. the IP3 pathway is within the cell. It reacts with the G protein, and it's the phospholipodiesterase or something like that. Anyways, but the thing that we need to know is that the ones on here are alpha 1, delta 1, M1, and we'll just do this, M1, M3, and M5. And like I said, these are excitatory, so they will all excite them. And then this one lowers the cyclic AMP within the cell. And so that will be alpha 2, delta 2. Actually, this delta does not belong here. It's just those. Delta 2, and then M2 and 4. And like I said, these are inhibitory, so they will stop that action potential from taking place. And then on this one, we have all of the betas. So we have beta 1, 2, and 3, and then delta 1. And so somehow, even though with this increase in cyclic AMP, the beta 2 is an inhibitory, but the rest are excitatory. So we do follow this rule that if they're odds, they're excitatory. If they're even, they're inhibitory. Yeah. So when neurotransmitters bind to these, it's an excitatory. So for example, an alpha 1 is in your eye, and when norepinephrine binds to it, it causes a dilation, so your pupils get bigger. For example, in the lungs, if you're having like an asthma attack, or the soft muscle within your throat is constricting, a way that we fix that is by enhancing the beta 2 on your throat. And so since it's inhibitory, it'll actually relax your throat muscles. So we can see that these different things are important for keeping balance in our body. So that's like the sympathetic, parasympathetic. When one's too low, the other one helps it out, or if the other one's too high, the other one balances it out. So that way it's not too much and it doesn't destroy our system or kill us or anything like that. So yeah, so that's kind of everything for the autonomic system, somatic system. We get to see the neurotransmitters, how they work, how does the system run together, how do they fit together, and so we can kind of see their relationship with each other. So thank you for watching.